Combining functions. When given two functions, we can combine functions in a multitude of ways. The first four are the basic operations of mathematics. So if we're given two functions f and g, we can add the functions together, we can subtract, multiply, or divide the functions. Now in each of these cases, the definitions for these are rather obvious. So the sum function, f plus g of x, is defined as f of x plus g of x. And the domain of this function will be the intersection of the domains of each of the individual functions f and g. Likewise, the difference function, f minus g of x, is simply the difference f of x minus g of x. Now it should be noted here that if you do g minus f, that would be different. That would be g of x minus f of x. The product function, fg of x, is simply f of x times g of x. And the quotient function, f over g of x, is f of x divided by g of x. And in each of these, the domain is the intersection of the domains of the independent functions. And for the last one here, we get the additional restriction that g of x cannot equal 0. Let's take a look at an example. So here we have the function f of x equals 1 over x minus 2, and g of x equals radical x. In this case, we want to find the four functions here, the basic operations, f plus g, f minus g, f times g, and f divided by g. So let's go ahead and go through that. So f plus g of x is defined to be f of x plus g of x, and f of x is 1 over x minus 2, and g of x is radical x. Now you could combine these together by getting a common denominator. In this case, I won't. I'll just leave it as is. But then what about the domain? So let's think about the domain of f of x and the domain of g of x separately. So for f of x, it's pretty clear that x cannot be equal to 2. And for g of x, since we're taking the square root, we cannot take the square root of a negative number, so x must be greater than or equal to 0. So when we think about the domain of f plus g, we have to take both of these into consideration. So yes, it is true that x must be greater than or equal to 0, but it is also true that x cannot be equal to 2. So if I look at that domain on a number line, here's 0. We know that x is going to be greater than or equal to 0, so that's all of these values over here. But at x equals 2, we cannot plug in that number, so we have to exclude that number. So we're going to have a parentheses here and a parentheses here, and the domain is going to be all the numbers between 0 and 2, including 0, but not including 2, and then also all the numbers greater than 2. So the domain here in interval notation would be all the values from 0 to 2, union all the values from 2 to infinity. And in each of these cases, we are not including 2. For f minus g of x, it's basically the same thing. It's just subtraction. So it's f of x minus g of x. So this will be 1 over x minus 2 minus radical x. And the domain will be the same domain. For the third part, f times g of x, this will be 1 over x minus 2 multiplied by radical x. And in this case, we can simply think of radical x as being radical x over 1. And if we multiply straight across here, we get radical x over x minus 2. And the domain will be the same once again. Now finally, for the last one, we have f over g of x. Now f, of course, is 1 over x minus 2, and then we're dividing that by the square root of x. Now this is the same as 1 over x minus 2 multiplied by 1 over radical x, which can be simplified into the following. Now, the domain, we have one additional restriction. So if you look at the domain up here, please notice that it is no longer okay to plug in x equals 0. Because if you plug in 0 here, the square root of 0 is 0, and we will be dividing by 0. So we get an additional restriction that x cannot be equal to 0. So the domain here will be basically the same as above, but we now have a parentheses on 0 because it's not included. Now for part B, it's asking us to plug the number 4 into the sum function, the difference function, the product function, and the quotient function. So since we've already done the work of finding these functions, to do part B, all we have to do is plug in the number 4. So if I want to do f plus g of 4, all I need to do is go to f plus g of x, which is this function right here, and then we just plug the number 4 in there. So this would be 1 over 4 minus 2 plus the square root of 4. This is 1/2 plus 2, which is 5/2. For the next one, f minus g of 4, it's exactly the same thing, just with a minus sign here. And so that's going to be 1/2 minus 2, which is negative 3/2. For f times g of 4, we're simply going to plug 4 into the product function right here. So that will be the square root of 4 divided by 4 minus 2, which is 2 divided by 2, and that equals 1. And finally, f divided by g of 4 is just plugging 4 into here, and that will be 1 over the square root of 4 times 4 minus 2. This is 1 divided by 2 times 2, which is 1/4. Functions can also be added graphically. So let's consider the graphs of f and g are given here. So here is y equals g of x. Here is y equals f of x. What would the graph f plus g look like? Well, basically all you're doing is for every value x on the x-axis, you're taking the y value of g and you're adding to it the y value of f. So in this case, we're just going to take this little bit of extra y value and add it on to the g of x. And so what it does in this particular case is it makes the graph a little bit higher. And you can see that if you do that all the way across, you will get this new graph, f plus g. Now, this is a tedious way to graph the sum of two functions, but you should understand that all you're doing is adding the corresponding y values. Now let's move on to the composition of functions. Given two functions f and g, the composite function f of g, also called the composition of f and g, is defined to be f of g of x. So this little circle thing here represents the composition of two functions, and the way you do it is you plug the second function here into the first function. So we're plugging g into f. Now, what is it exactly that you're doing? Well, if you think about it, when you're given an x value, what you're doing is you're plugging that x value into the g function first. So if I start with an x value here, the g function is going to take that to a new value, which we're going to call g of x. And then once I have g of x, that value gets plugged into the f function. And then that f function is going to take that value to another new value, which we call f of g of x. Let's take a look at an example. So in this problem, we have f of x equals x squared and g of x equals x minus 3. We want to find each of the composition functions. So we want to find f of g of x, and we also want to find g of f of x. Now, f of g of x, the meaning is that we are plugging g of x into f of x. So in this case, to actually figure it out, you could simply say we know g of x is x minus 3. So I can replace g of x here with x minus 3. So this becomes f of x minus 3. And of course, this means we're going to take x minus 3 and plug it into the f function. So we're going to replace the x here with x minus 3. And so this becomes x minus 3 quantity squared. Now g of f of x is just the other way around. So now we are plugging f of x into g of x. And so since f of x is x squared, this is equivalent to doing g of x squared. And in this case, we're taking x squared and we're plugging it into here. And if you do that, of course, you are going to get x squared minus 3. So the first thing to notice when you do the composition one way versus the other way is you should notice that they are not the same. Okay, so f of g is not equal to g of f. Now, I'm not saying that they're never equal. I'm saying that they are not equal in general. There are some cases where they are equal. Now, in terms of the domain, basically you have to take all of the values in the domain of the inside function, and then you have to think about what might be restricted when you plug those values into the outside function. Now, in this case, the domain is very simple because the domain of g is all real numbers, and the domain of f is also all real numbers. So the domain for each of these composition functions is simply all real numbers. Now, what about part B? It says to find f of g of 5 and then g of f of 7. So for part B, to do f of g of 5, let's just note that we already know that f of g of x is x minus 3 quantity squared. So all I'm doing is I'm taking the number 5 and I'm plugging it into this function. And so that is going to be 5 minus 3 squared, which is equal to 2 squared, which is equal to 4. Now, we also could do this a different way. So when we have f of g of 5, we could use the definition, which says that it's equal to this. And then we can just figure out what is g of 5. So remember, g of x was x minus 3. So if I plug 5 in there, I get 5 minus 3, which is equal to 2. And then this just becomes f of 2. And f of x is x squared, so that just becomes 2 squared, which is 4. Same answer either way. In this case, it's a little easier to do the first method since we already know what that composition function is. Now for the second one here, g of f of 7, it's the same idea, except that now we are plugging the number 7 into the g of f function. So we're plugging 7 into here. And so this will be 7 squared minus 3, which is 49 minus 3, which is 46. Now, of course, we could do it the other way, and maybe if you want, you can do that on your own to verify that you get 46 either way. In our next example, we're going to get a little more practice finding compositions. So in part A here, we have f of g. Now let's keep in mind that f of g of x means that we are plugging g of x into f of x. Now, g of x is this thing here. So this becomes f of the square root of 2 minus x. Now we're going to take the square root of 2 minus x and we're going to plug it into here inside the f function. So that's going to give us the square root of the square root of 2 minus x, which is a little bit strange, I suppose. Now you could leave your answer like this, but if we remind ourselves that the square root is a 1/2 power, then the square root of 2 minus x can be written as 2 minus x to the 1/2 power. And then that is also raised to the 1/2 power because we have another square root on the outside of that. And when you have a power to a power, you multiply those powers. And so this becomes 2 minus x to the 1/4, right? 1/2 times 1/2. And that actually could be rewritten using an index of 4. So this is probably the best way to write it, but I mean, technically you could leave it like this, but this does definitely look better. Now, what about the domain? So for the domain, let's keep in mind that our inside function, g of x, already had a restriction. So g of x is the square root of 2 minus x. We know that no matter what, 2 minus x has to be greater than or equal to 0, right? Because you're not allowed to take the square root of a negative. And this says that 2 is greater than or equal to x, or x is less than or equal to 2. Now, do you get any additional restrictions after you plug g of x into f of x? Well, if you look at your final function here, you have once again an even root. And when you have an even root, whatever's inside must be positive. But as long as x is less than or equal to 2, this is going to be positive. So our domain here is going to be all values from negative infinity up to 2, which is just an interval notation way to say x must be less than or equal to 2. Now for part B, we're going to do g of f. Now g of f, of course, is just the other way around. This is going to be g of f of x. And of course, f of x is the square root of x. And so this becomes g of the square root of x. And that means we're going to take this function and plug it into here. And so that's going to give us the square root of 2 minus the square root of x. Now, that cannot be simplified, but what about its domain? Well, first, let's consider the inside function f of x, which is equal to the square root of x. We know the domain for this function is all values from 0 to infinity, right? Because you cannot plug a negative number into here. But do we get any additional restrictions? Well, if you think about it, we do. Because, for example, if I plug in a number like 9 into x here, the square root of 9 is 3, and 2 minus 3 is going to be a negative number, and we cannot take the square root of that negative number. So we're going to have additional restrictions on top of the fact that we know x has to be positive. To figure this part out, we'll just take the inside here, which is 2 minus radical x, and we'll remind ourselves that this needs to be greater than or equal to 0. And this means 2 must be greater than or equal to the square root of x, or the square root of x must be less than or equal to 2. Now, if you square both sides, you'll see that x must be less than or equal to 4. So this is an additional restriction on top of the fact that x already has to be greater than or equal to 0. So our domain here is going to be all values greater than or equal to 0, but less than or equal to 4. So it will be all numbers between 0 and 4. For part C, we're looking for f of x. And f of x means we are plugging f of x into itself. Let's remember that f of x was the square root of x. And so now we are plugging the square root of x into the square root of x. So this gives us the square root of the square root of x. And just like before, we can change this into the fourth root of x. Now for the domain, we already know that x has to be a positive number, or at least a non-negative number, right? We know this from our work up here. And when you look at the final function here, you do not get any additional restrictions, because as long as you're plugging in a positive number here, you can take the fourth root, no problem. And also 0 is okay. Now for part D, we are doing g of x. This means we are plugging g of x into g of x. Now let's remember that g of x was the square root of 2 minus x. So we're doing g of the square root of 2 minus x. And that means we're plugging the square root of 2 minus x into the square root of 2 minus x. So this becomes the square root of 2 minus the square root of 2 minus x. Now what about the domain? Well, again, for g, we already established that the domain has to be a number between negative infinity and positive 2. But do we get any additional restrictions? I suspect we do, because whatever we plug in for x, this quantity must also be positive. So 2 minus the square root of 2 minus x must also be greater than or equal to 0. And this means 2 must be greater than or equal to the square root of 2 minus x. Or I can write that as the square root of 2 minus x must be less than or equal to 2. If I square both sides, I get 2 minus x is less than or equal to 4. And now if I just solve for x, I can subtract 2 here. And then when I divide by -1, I'm going to get x is greater than or equal to -2. So we already know on our number line, the original domain said that x could only be these values. But now we find out that in addition to that, x must be greater than or equal to -2. So the domain here has to be all numbers in between -2 and +2. Compositions can be applied to more than 2 functions. So for example, if we have the 3 functions f, g, and h, we can find the composition f of g of h of x, and this would be defined to be f of g of h of x. So the way you would do this is just start from the inside and work your way out. So this would be f of g of h of x is x plus 3. And this means we are going to plug x plus 3 into g of x. So we're going to take this function here and plug it in for x right there. Now when we do that, we're going to end up having f of x plus 3 quantity to the 10th power, right? Because that's what you get when you put this into here. Now we're going to do f of that thing. Now f is defined to be x divided by x plus 1. So this x plus 3 to the 10th power is going to take the place of both x's here. And so this would be x plus 3 to the 10th power divided by x plus 3 to the 10th power plus 1. And this would be our triple composition here. You should also be able to recognize a composition of functions. So if you're given capital F of x is equal to the 4th root of x plus 9, you should be able to find 2 functions f and g such that when you do their compositions, you get the function here. Now the way to think of this, if you're going to think of capital F of x as being f of g of x, you should think of your g of x as kind of being your inside function and your f of x as being your outside function. So if I let f of x equal the 4th root of x, and if I let g of x be equal to x plus 9, you should be able to see that if you take x plus 9 and you plug it into here, you will get the function that you have here. So one possibility is that we define little f to be the 4th root of x and g to be x plus 9. Now, just to be clear, we don't have to do it this way. There are actually infinitely many different choices that you could make for an f and a g that would give you the same function when you do their composition. But this is definitely the most obvious choice. And finally, let's look at an application of composition functions. Suppose a ship is traveling 20 miles per hour parallel to a straight shoreline. So we have a straight shoreline here, and we have a ship traveling parallel to that shoreline. The ship is 5 miles from shore, so that's the perpendicular distance from shore there. And it passes a lighthouse at noon. So straight off of the shore here at noon, it passes this lighthouse. What we want to do in part A is express the distance s between the lighthouse and the ship as a function of d, the distance the ship has traveled since noon. So since the ship is traveling in a straight line like this, d will be this distance traveled, s will be the distance from the lighthouse to the ship, and of course this distance here is always 5 miles. So you can see we have a right triangle here. And we know that in a right triangle, we can apply the Pythagorean theorem. So we know that 5 squared plus d squared must be equal to s squared. So if I want to express the distance s as a function of d, I'm just going to solve for s by taking the square root of both sides. Now if I bring this over to the left side, we're going to get s, and then square root of 5 squared is 25 plus d squared. And so here is s as a function of d. Now for part B, we want to express d as a function of t. So the distance that the ship travels as a function of time. Let's keep in mind that the ship is traveling at 20 miles per hour. So the distance that it's going to travel is simply going to be 20 miles per hour multiplied by the number of hours. And t is going to be the number of hours that it's been traveling. So we know that d must be equal to 20 times t. And this is just because distance is equal to rate times time. So now for part C, it says find f of g. What does this function represent? So let's keep in mind that f was the first function that we found. G is the second function that we found. So if we want to do f of g, and this will be f of g of t, we're basically going to take the 20t and substitute it in for d right here. And this will give us the square root of 25 plus 20t quantity squared. And if we simplify this a little bit, we get the square root of 25 plus 400 t squared. Now, what does this represent? Well, keep in mind that this represents s, which is the distance between the ship and the lighthouse, but now it's expressed as a function of time instead of as a function of d. And that concludes this video lesson.